All right, so today we are going to connect our knowledge about special right triangles to what we call the unit circle. So the unit circle is basically a mapping of all sorts of different triangles and different positions that represent different degree measures of a 360-degree circle on the coordinate plane that has a radius of 1, okay? So if we have a circle with a radius of 1 and a center of 0, 0, it's basically going to be a circle that's right in the middle of the coordinate plane. And there's going to be different degree measures within that circle, and we're going to talk about those and how it translates to the 30, 60, 90, and 45, 45 triangles. So before we do any of that, let's go ahead and refresh our memory about these special right triangles. So for the very first one here, the 45, 45s, what do we call the hypotenuse on this one?
2L.
Not 2L. L
Square root
2, and the other two sides are
L.
L and L, because this is a right isosceles triangle, right? Now for the 45, 45, I think you guys said that the other answer here, what's the hypotenuse here?
L square root 3.
No, 2L,
Oh, yeah.
but you're right, it's the 60, which is L square root 3, there you go, and then what's this side here?
L square root 3.
L, just regular L, okay? So those rules will allow you to find the missing sides of any 30, 60, 90, or 45, 45. If we know one side, we can find all the sides with that formula, right? Because they're all in terms of L. So what we're going to do is we're going to do that exactly for these triangles. So as you can see, this is a 30, 60, 90 triangle. Of course, this is 60, right? You can label it if you want. I would label this side 2L, right? Because it's a 30, 60, 90. So that means L would be what?
1. No, 1.5.
1/2. I divide by 2, right? So that's L. What side would be L?
Adjacent side of the opposite right angle.
Okay, yeah, this one here, across from the 30, right? Because that would be just plain L. And this side is L times radical 3. So 1/2 times radical 3 is radical 3 over 2. Okay? So this right here is basically going to be the mapping of things that we learned from the unit circle. So the next one is the 45, 45. So we can label this side that we know, this is the radius of the circle. Essentially, we can label it what? L square root 2. In order to solve in math, to reverse multiplication, I do what? Division, right? So L radical 2 is equal to 1. I want to solve for L. I divide both sides by radical 2, right? But in math, we can't leave a radical in the denominator, so what do I do next? Multiply the top and the bottom by? That's called rationalization, which leaves me with radical 2 over 2. So this side is radical 2 over 2. And what's this side over here? Same thing, because we know that these triangles are right isosceles, so the two sides are just plain L. So does everybody see how we got that? Okay. Rationalization, that just means you get the radical out of the denominator by multiplying by the same thing on top and bottom. Okay, now if I zoom out here, what do you notice about the first and the third triangle?
They're the same triangle.
They're the same triangle, but they've been positioned differently. So this one across from the 60 is going to be radical 3 over 2. The one across from the 30 will be 1/2. Cool. So now that we have all the triangles filled out, let's go and do the sine cosines of them. Okay. So we know about sine and cosine. We know about the relationship. We know about the opposite over hypotenuse, the adjacent over hypotenuse, all that stuff, right? So if we're talking about sine of 30, 30 is my reference angle in this question, right? Because it's saying sine of 30. We know that sine is what over what?
Over h. Opposite over hypotenuse.
Opposite over hypotenuse. What is my opposite side here?
1 over 2.
1 over 2 over the hypotenuse, which is?
2. 1.
Square root 3.
Okay, let's I don't know, I heard a lot of different stuff. So it's opposite, which is this side,
Yeah.
over the hypotenuse, which is 1. What's anything over 1?
1.
The same
No.
thing.
Same thing.
Itself? Okay. No, it's okay. It's a lot of quick thinking here. So cosine is what over what?
Adjacent over hypotenuse.
Good. What side is adjacent to the 30 degree?
Square root 3 over 2.
Through square root 3 over 2 all over the hypotenuse, which is 1. Make sense? Okay. Next one. Sine of 45. Does it matter which one angle I use here? No, because they're both what? The same. So if I use this one, opposite is radical 2 over 2. Hypotenuse is 1. Remember, I just use this as a tool to get there. So hypotenuse is 1. So anything over 1 is just itself, right? Now, we know that cosine is adjacent over hypotenuse, right? So you're going to notice the adjacent side and the opposite side in this case are the same. So what this means is if you put sine of 45 in the calculator and cosine in 45 in the calculator, you're going to get the same answer, okay? And that's why. Over here, if you put sine of 30, cosine of 30, you're going to get those answers. Now, the reason this is so essential, this procedure, and I'll zoom out because you guys are still writing stuff. The reason that this procedure is so essential, you could do sine in the calculator of 30 and it would give you 0.5, which you know is 1/2. But if you try to do cosine of 30 in the calculator, it's not going to look like this. What is it going to look like in the calculator? Does your calculator, unless you have one of those fancy ones, it usually gives you a decimal, right? This would just give you a decimal approximation. So that's why it's so important we do this. You have to know what's called the exact value, which is radical 3 over 2. Okay? So that's the reason that we do all of this. Now, what you're going to notice is we talked about this earlier. The first and the third triangle here are the same, but of different perspectives. So what we're doing here is we're still finding the same things, but now we're doing sine of 60. So now we're doing opposite over hypotenuse, which in this case is radical 3. That was a terrible 3. Radical 3 over 2 over 1, right? Which is just radical 3 over 2 because it's over 1. And then cosine of 60 would be what? 1/2 over 1. So what do you notice about this, the 30 triangle and the 30s are angle, or the 60, about the sine and cosine?
They're the same thing.
Yeah, they're just flipped, which makes sense, right? Because the triangles are flipped as well. And with the 45s, they're the same because both angles are 45. So everybody good with that concept? Okay. Now, the most important thing here is for you to understand what these positions are. So I'm going to explain to you briefly about what this picture is, what it means, all that good stuff. So this is essentially a triangle that's been drawn in the first quadrant. Okay, that's like the positive quadrant on both sides, okay? This right here is the radius of a circle that's been drawn on the coordinate plane, okay? So just to be clear, you don't have to draw this on yours, but just so you understand what's happening, this is as if I had a circle in the quadrant. That was the worst circle ever, but you get the idea. A circle where the radius is 1, okay? This right here, also you could think about it as if this is our initial side. Can't draw today. If this is our initial side, right here, if we open it up, this is our terminal side, which creates a 30-degree angle, right? So this 30-degree angle that we create is created by, you need your paper? I think Rodrigo has it. So the angle that we created is a 30-degree angle, okay? So in this case, what we have to do is we're going to figure out what the side measures are. Now, what you're going to notice is, isn't this triangle the exact same as the triangle right here? You see that? It's just been inscribed in the unit circle, or in the coordinate plane. So in this case, we have to just write those side measures in there. So we know that this side is what? According to what you just did above on the left. This side is radical 3 over 2, and this side is 1/2, right? So if you're trying to find the coordinate on the side of the circle, let's think for a second. And this kind of gets a little squished, so I apologize. If we're thinking about a coordinate on the side of a circle, or a side of a thing, what do we know the coordinate system is in the coordinate plane? What comma what? X comma y, right? X represents horizontal distance to get to that point. Y represents what? Vertical distance. What is the horizontal distance to get to that point? radical 3 over 2. What is the vertical distance to get to that point? 1/2. So that's the ideology behind every coordinate on the side of a circle. So if you want to find the coordinate of any circle, any point on a circle graphed in the coordinate plane, this is how you could do it, using basically 30, 60, 90 triangle rules, or whatever type of triangle it is. All right, now that we're good with that, let's talk a little bit about if we were to inscribe all of these triangles inside of a circle. So what you're going to notice here in this drawing, what do you notice about the hypotenuses? I don't know what the plural is. Whatever it would be. The plural hypotenuse in this picture. What do you notice about all the hypotenuse? They all go to the edge, and then this right here would be the radius of the circle, correct?
Yeah.
Isn't this also the radius of the circle?
Yeah.
And the radius of the circle?
Yeah.
And another radius?
Yeah.
And a radius?
Yeah.
All the radii are the same what?
Like,
Length. For any given circle, the radius of that circle given at any value is always the same value, okay? And the radius of the unit circle, if there's one thing you know about the unit circle, the radius is always 1. So you're working with a situation where the radius of that circle is always 1. And because of that, that's where we come up with the fact that we do all of those triangles. Notice on the problems that we were doing, the hypotenuse was always 1. That represents the radius of the unit circle, okay? So now that you have the idea, these 3 triangles represent, if I opened up 30 degrees, the next one represents if I opened up an angle of 45 degrees, and the last one represents if I opened up an angle of what? 60 degrees. That's where those triangles come from, opening up different angles of the circle, okay? Now, before we go into doing the unit circle, I want to just give you a little disclaimer, okay? This is a topic that's very different than anything you've ever learned, okay? We're going into a trigonometry viewpoint here. Most of the stuff you've been doing, even in geometry, is algebra-based. You've seen a little bit of trigonometry, but this is very different. So I just want you to realize that it sometimes just takes time to understand. It's a different way of thinking. So don't be discouraged. We're going to take a lot of time to dissect this topic. This is just the introduction. So if you don't feel like you got it 100% by today, that's okay. All right? So I don't want anybody to feel like discouraged or worried if they're not getting it on day 1. Okay? It takes time. I promise you will get it. So what we're going to do right now is we're going to just find the degree measures of the unit circle. Okay? So go ahead and open up to this page on your notes. Guys ready? Okay. So this line right here, okay, I'm not going to do this on every single one because I'll get too cluttered on here, but this is our initial side. I'm just drawing really poorly today, but this is our initial side. And then I open up my terminal side as if I opened it up 30 degrees. So this point on the side represents opening up 30 degrees of the circle from that initial side. Okay? The next one represents as if I opened up an angle of 45 degrees. Okay? Angle of 45 degrees. The next one represents if I opened up an angle of 60 degrees. Okay? This is like me opening up an angle. This is 60 degrees. That means that this is 60 degrees of opening. You guys see what I'm saying here? Okay. Now, for the rest of it, and I'm going to talk you through the triangles as well. I could draw a triangle right here. That's 30 degrees here. Okay? And wouldn't that represent a 30, 60, 90 triangle if I were to open it up? Now, I could also have drawn a triangle right here, which would create a 45, 45, okay? So, not to get this too cluttered, but you're essentially creating those triangles in the unit circle. So I have the 30 degree one, I have the 40 degree triangle, and I have the 60 degree triangle as well. Now, those triangles could be drawn in any of these quadrants, right? I could draw a 30 degree triangle over here. This would be 30. I could draw a 30 degree triangle down here and over here. What do you notice when I draw all 4 types of quadrantal triangles? What kind of shape does it create? It's a bow tie. So if you look at all of the types of triangles that we could create in each of the quadrants for any of the given degree measures, it's going to create a bow tie shape. Okay? And that kind of helps you construct that triangle. So with the 45s, I could do the same thing. I could create a 45-degree triangle here, here, and here. Okay? So I could create one here as well. I could create one out here too. And that would be a 60, and so on. So notice the bow ties are going to get like more tall, okay, bigger the degree measure is, all right? So I want you to think about it this way. Let's talk about the 30-degree triangle in the second quadrant, okay? If I wanted to create a 30-degree triangle, remember we're always opening up an angle from the initial side, so I'd have to open up the angle this much, okay, right? So what would be the degree measure over here?
Oh, it would be 30.
This piece would be 30. What'd you say? 150 minus 180. Yes, good. So that would be 150 degrees. I'd have to open up to create that 30-degree triangle in that quadrant. Do you guys see what I'm saying? Okay. Now, you don't have to draw all this because it could get a little cluttered on yours, but what if I wanted to create a 45-degree triangle in this quadrant? I would have to go out this way, right? 135, very good. So if you're wondering how he got that, it's basically 180 minus that angle measure, right? Because we have the 45-degree piece here, so we have to open up the supplement of that. I guess that's the right mathematical word for it, the supplement, because it is 180. And then, lastly, if I wanted to create a 60-degree triangle in here, if this piece is 60, that means that this outer piece must have been, somebody said it, 120. So, what you're going to notice, and I'll start creating these rules out here, if we want to create a triangle in the first quadrant, the angle is whatever the angle is. If it's a 30-degree angle, it creates a 30-degree triangle. It's exactly as you expect, okay? If I want to create a triangle in this quadrant, what's that noise? Oh my gosh, that scared me. I was like,
Wait,
so,
that way, what?
the noise.
Oh, was it really loud? Oh,
Yeah.
my fault.
So in this quadrant over here, if I want to create a triangle of that size, I have to do 180 minus the angle measure in the triangle to get with the degree measure. You guys see what I'm saying? To get those angles. Okay. So now we're going to move on to the third quadrant down here. So in the third quadrant, I start at the initial side, and if I want to do the 30-degree triangle, I have to open up to here, right? So in order to do that, I go a full 180 and an additional what? 30 degrees. So what's 180 plus 30? 210. If I want to create a 45-degree triangle in this quadrant, I go 180 plus, you're right, 225, 180 plus 45. And then in this, to do the 60-degree, I would do 180 plus 60, which is 240. So the rule in this quadrant is you take 180 and you add the angle measure to it to get that particular degree measure. Okay. Now, if we're talking about the fourth quadrant, we start at the initial side, and now we have to open all the way here to get to the 30-degree. So all we have left here is the 30-degree angle. So I had to go all the way around to go 30 degrees. What would that be for the 30-degree? 330. I would have to subtract from 360, right? How would I get the 45-degree? I'd have to open up all the way around and leave 45 degrees left, which would be 315. And then lastly, for the 60, open all the way up but leave 60 degrees left, which is 300. So what do you think the rule would be for this quadrant? 360 minus the angle. Make sense? You could do, I suppose, 270, but I would do the 360 rule. All right, any questions about that? Okay, so you know how the other day we learned about converting degrees to radians. So with the unit circle, you have to also know what the radian measures on this thing is. So you know that if I gave you the degrees right now, you could convert all of those to radians because you do know how to do it. But I do want to show you some like fast track ways to do it without having to basically do every single one of those calculations every single time. So, because you are going to have to be able to produce one of these unit circles on your own for the quiz, test, quiz, whatever you want to call it. So we have this, and as I do it, I'm going to write the degree measures in 2 just so you know what's happening. So 30 degrees, I would multiply it by pi over 180. I would simplify, and I would get pi over 6. Now, we know that an entire circle is always 2 pi radians, okay? 2 pi radians. That represents a whole circle. So you don't have to write this, but just to think about it, that means that if I open up 30 degrees of the circle, that means that that represents a 1/12 of the circle. That angle I opened up is exactly 1/12 of the circle that I opened up. Does that make sense? Okay. So all of these can be represented in that way, a portion, a percentage or decimal or fraction of a circle. So the next one we know is 45. So I can take 45 and I can multiply it by pi over 180, which gives me pi over 4. And you can just trust me on the calculations. I think I did this one in green last time, so sorry, I meant to keep them the same color. So this one is going to be pi over 4. Does everybody see how I got that? I just multiply by pi over 180. And what's the next one here going to be?
Pi over 3.
Good, 60 degrees, which I can multiply by pi over 180, which is pi over 3. Bless you. So the reason that it's pi over a number is because as we go through, we're opening up and creating a bigger section of that circle each time, which represents a bigger proportion of that circle that we're creating in that like pie slice almost. So in the other quadrants, we know that they are manipulations of these other degree measures, right? I know that this one is 150 because it's another version of the 30-degree triangle in another quadrant. Had to open up a bigger angle. Yes?
Wait, so, I mean, isn't pi in this situation just equal to 180 since you're doing pi over 3 equals 60 degrees?
You can, that's a way to convert from radians back to degrees. Yes, that's a shortcut. So that's a good observation, yes. Essentially, pi radians is 180 degrees. So yes, sort of, if that makes sense. So 150, how could I go from 30 degrees to 150? Multiply by? 5. So can't I just simply multiply the radians also by 5? So it would be 5 pi over 6. That's a quicker way to do it than having to do all that math every time. Okay. This one right here is 135. What would I multiply 45 by to get to 135? 3. So what's the radian measure going to be?
3 pi over 4.
Good. Now for this one, this is 120. I keep mixing up my colors. I'm sorry. What would 120 be?
2 pi over 3.
Yeah, 2 pi over 3. Or no, it's just, yeah, 2 pi over 3. You're right. Sorry. 2 pi over 3. It's supposed to be green. Gets confusing after a while. So this one here is another version of the 30-degree triangle. It's a 210. What can I multiply 30 by to get me to 210?
7.
So 7 pi over 6. This one here is 225. What could I multiply 45 by to get to 225? 5. So it's 5 pi over 4. And then lastly, this is 240. What can I multiply 60 by to get to 240?
4.
So it's 4 pi over 3. And then the last quadrant, this right here is going to be our 300. What could I multiply 60 by to get to 300?
5.
So 5 pi over 3, good. What could I multiply 45 by to get to 315?
7.
Good, 7 pi over 4. And then lastly, what can I multiply 30 by to get to 330? 11. Get 11 pi over 6. So when you do the memorization aspect of this, I recommend only really memorizing the first quadrant, and then everything else kind of follows from that rule. Okay, did you see how we were able to use the first quadrant to get the other ones? Okay. All right.
I missed the last one. What was the last one? 3:30.
You're welcome. All right, you guys can explain it to each other at the end. Let me finish. So, this right here is going to be the unit circle. Quadrant number 1. Okay, quadrant 1 is going to be the one that's positive for the x and the y. Okay, so what we're going to fill out on the unit circle is like a standard unit circle. It's always going to have degrees, it's going to have the radian, and then the coordinate. That's a standard unit circle. Okay, so we know that the degree measure at this piece is what? We've done it a few times here. 30. The radians is pi over 6. The next one is 45, pi over 4. And the next one is 60, pi over 3. Now these ones here are a little bit different. If I didn't go up at all, if I didn't change my angle from the initial side, what's the degree measure? 0, or I guess I put it in the wrong spot, but that's also right. We'll get to that. It's the radian. 0 degrees is the same as what? 360. So 0 radians, of course radians is 0 too. What would be the radian version of 360? 2 pi.
Wait, how'd you get that?
Just you convert it, 360 times pi over 180.
Oh, okay.
All right, so now we're going to talk about coordinates. So remember, the unit circle always has a radius of what? 1, very good. So if this is a radius of the circle, which it is, what's going to be the coordinate here?
1, 0.
1, 0. Now up top, this right here is how many degrees? 90, which is what in radians? Pi over 2, very good. Because it's a fourth of 360 is one way to think about it. Now, if this is the radius, which is the height in this case, what would be the coordinate? 0, 1, I think somebody said it. Good job. Now the other ones are a little bit more tricky, but not too tricky. On the very first page, do you remember how we created a triangle here, and we showed how the coordinate has to do with the x and the y distance of that triangle that is created here with the right angle and all that? Okay, so this is a 30, 60, 90 triangle. Here we go again. If this is the radius, which is 1, what's going to be this side measured on here, the horizontal distance? Radical 3 over 2. I'm just taking that triangle we did on the first page and reiterating it in here. This right here, the height is going to be 1/2. In math, the coordinates go x, y. X represents horizontal, which is radical 3 over 2. Y represents vertical distance, which was 1/2 to get to that point. Now, with the 45, 45, what do we know about the horizontal and vertical distance with a 45? They're the same. They're both L, which in this case is what? Radical 2 over 2 for both of them. Notice that the hypotenuse is never used in the coordinate. It's always the 2 legs. You see that? Because the hypotenuse represents the diagonal, which is what we use to get the other values, but we don't want the diagonal, we want the x and y. And then we know 60 is the same triangle as the 30, 60, 90, but what's the only difference? X and y get switched. So that is how you start creating a unit circle based on those triangles. Make sense? Hopefully a little bit? Okay. So all you have to do this weekend is, I can't ever check this, so you could not do this, but I recommend it. I would look over the unit circle for 10 or 15 minutes.